confidence sets, we're going to do a major change, which is going to shift from parametric inference to non-parametric inference. So I guess that'll be next week. So let's continue with these confidence sets. Let me review what we started with at the end of last class. We're going to construct a set. Often it's an interval, but it doesn't have to be an interval. And we want the probability that the random interval traps the fixed parameter value to be at least 1 minus alpha. Alpha is alpha is the number you pick, say 0.05. So this would be called 95% confidence set in that case. But it's got to hold for every distribution in your model. So in other words, the minimum of this has to be 95%. This is called the coverage of the confidence set. How often it covers the value. So we're going to start by constructing an example. And a couple of examples, then we'll talk about how to do it in general. And so before I do that, any questions? All good. All right. So let's start with our one we often start with, which is the normal distribution. I'll take sigma known first. So what's our set going to look like? Well, our set, in this case, we're going to take to be an interval, LU, for lower and upper. But keep in mind that these are functions of the data. In fact, let's say what they are. We're going to take L to be x bar minus C, and U to be x bar plus C. So I'm just going to take x bar plus or minus some constant C. What's the constant C? Well, let's figure out what it has to be. So the probability under the true value, and this has to, remember, the result has to hold no matter what the true value is, because we don't know what the true value is. So I want the probability of the true value that theta is trapped between L and U to be 1 minus alpha. And again, these are random, and this is fixed. So that's the probability that x bar minus theta plus C. And now I'm going to just sort of rearrange things a bit here. I'm going to subtract. Let's subtract x bar. So theta minus x bar. And I'm trying to get it to look like something familiar. So we're used to seeing x bar minus theta. So let me write that as, let me multiply b by minus 1. So it becomes so this became c bigger than or equal to x bar minus theta bigger than minus c, and then I just wrote it the other way. And then I'm just going to multiply by root n. That's a familiar thing. And heck, we might as well also divide b by sigma while we're at it. Now, we've got this thing, and it doesn't matter what value theta is, because x bar minus theta is root over sigma. We know what that is. It's exactly normal, 0, 1. Right? This is exactly equal to the probability where Z almost 0, 1. So if I think about a normal, and I'm trying to find, I want this to equal 1 minus alpha. And this is root n C over sigma. This is minus root n sigma sigma. I know what this has to be then, right? For this to be alpha, this better be that Z sub alpha over 2, and this better be minus Z sub alpha over 2. So I have to set root n C over sigma to be Z alpha over 2. So I can solve for C. C is sigma and U is. So the condition that it have 95% coverage, or 1 minus alpha coverage, tells me I can C. And so there we're done. The confidence interval is x bar plus or minus sigma over root n Z alpha. Let's think you again about the interpretation. So this interval is very simple. I just take x bar plus or minus this thing. And imagine repeating this experiment. So I know theta, I give you some data, you don't know theta. But you can compute this. And if we were to repeat this game over and over again, your interval would contain the true value 1 minus, with probability 1 minus alpha. And the nice thing about a confidence interval is it's giving you some idea of how precise your answer is. A point estimator, x bar, is just a number. But you can see when this interval is wide, it means we don't have a very precise estimator, basically. But when x bar is a precise estimator, that would happen when n was larger or sigma was small. We're going to get it very narrow. So the nice thing about confidence intervals is it's in some sense telling you something about the uncertainty of your estimator. That's why it's much better to have a confidence interval than just a point estimator. It's much more informative. Okay. You can kind of guess one of the general methods now for getting a confidence interval. If we did exactly the same calculation with the MLE, so if I started with the fact that theta hat minus theta over the standard error, we know that's approximately 0.01 under certain conditions. If I did the same calculation then, I would get, in general, a confidence interval, which would be of the form the MLE, or any point estimator, plus or minus z alpha over 2 times the standard error. And what that confidence interval would be is an asymptotic confidence interval, in the sense that no matter what the true value of theta is, it won't be equal to 1 minus alpha, but it would converge to 1 minus alpha. That would be the confidence interval corresponding to the Wald test. So the point estimator is the MLE. The test you construct from it is the Wald test. The confidence interval you construct is the Wald confidence interval. Now let's getting ahead of ourselves because I just want to talk about what are the methods for constructing confidence intervals in general. Just as we had many methods of constructing, we also have many methods of constructing confidence intervals. And roughly, these are sort of overlapping. These are not necessarily, these categories I'm about to put down are kind of overlapping, but I'm going to say that there's 4 main methods. One is to use a probability inequality. The second one, which I think of as the most general method, it's called inverting a test. Remember I said that the most useful thing for tests, about tests, is that we're going to use them to construct confidence intervals. And I'll explain what that means here. Then there's something called pivot. And then there's large sample methods like I just described. But again, there's overlap because the test I invert might be a large sample test. So it's not, I'm not suggesting these are 4 separate methods, but just think of them as 4 themes here for how to construct confidence intervals. So let me start with probability inequality. What do I mean by using a probability inequality to get a confidence interval? Well, remember how we started the course. We started by doing these probability inequalities. And that can sometimes be a way to get a confidence interval, although I got to tell you, not very often. This is, I think, a sort of a division here between statistics and machine learning. Is that when I start talking about confidence intervals in machine learning, a lot of people say, oh, we should just use probability inequalities, but that actually doesn't work very often. So let me explain what I'm talking about. Remember Hoeffding's inequality. So suppose I have x1 to xn is Bernoulli with success probability p. What did Hoeffding's inequality say? It said that the probability that p hat, the sample average, minus p, being bigger than epsilon, look like this. If you think about it, this tells us how to construct a confidence interval. Because if I set this equal to alpha and find epsilon, then I know that if I take the interval p hat plus epsilon and p hat minus epsilon, this interval must be therefore a 1 minus alpha confidence interval, because the probability that this interval fails to trap p, the only way it can fail to trap p is if p is farther than epsilon from p hat. So the probability that this fails to cover it is precisely bounded above by this probability. If I set this equal to alpha, then I've got a 1 minus alpha confidence set. So if I solve for epsilon here, you'll get let's even call it epsilon sub n, because it depends on n. And so what that means is if I construct this confidence interval, p hat minus epsilon, p hat plus epsilon, it follows immediately from Houghton's inequality that the probability that that p is trapped in C is at least 1 minus n. So I have a nice simple confidence interval, and I didn't have to use any sort of limiting distribution or asymptotic approximation. So that's pretty good. That's a nice way to get a confidence interval. But it's not very general, because when you get to more complicated situations, usually if you write down these bounds, they often, first of all, they tend to be very conservative. They tend to get very, very, very wide when you do more complicated things. But what's worse is that in more complicated situations, these bounds often have constants in them. Start looking at some of these bounds that we derive. There's like a constant C1, a constant C. There could be various constants that appear in more complicated situations. And for proving theorem, that's fine. There exists some constants such that the following inequality holds. That's not good for a confidence interval, because then you're going to get a confidence interval that has these unknown constants in it. And you can't use the interval. And so this idea of using probability inequalities to get confidence sets can really only work in a few simple situations. So I wanted to mention that, but it just doesn't get used so often. For the second method is converting a test. So let me explain what I mean by that. What we're going to do, let me just explain it first in words, is I don't have a specific hypothesis to test. But what I'm going to do is pick every possible value that the parameter takes. I can take that as a null hypothesis and test that hypothesis. Is theta equal to 1? Is theta equal to 1.1? Is theta equal to 1.2? Just think of taking every possible value. Now I can say, every time I did a test, I either rejected it or I didn't. I'm going to collect together all the guys I didn't reject. And that turns out to be exactly a 1 minus alpha confidence set. There's a sort of duality between confidence sets and testing. So let me say that again. Imagine that for every value of theta, running out of symbols, let's say for every possible value of theta 0. So we're going to take theta 0 to be a null value, but we're going to let it vary now. We're going to take every possible value in the parameter space to be a null hypothesis. Well, let's fix one of them. Let's fix theta to be this, and we test. So when we do a test, we get the data and we make some decisions. So I'm going to describe that as a function. Let's say theta 0 takes the data, and it's either 1 or 0, which means reject or don't reject. I'll call this a test function. So you give me the data, I'm going to test this hypothesis. And let's suppose we've constructed it so it's test size alpha, so that the probability when we know is true of rejecting less than or equal to alpha. Probably equal to alpha, let's say less than or equal to alpha. So now what I'm going to do, here's a picture of what I'm going to do. I'm going to take the parameter space theta, and for every value, I'm going to say, I'm going to do a hypothesis test. Is this the truth? Is this? And every time I do it, I either reject or I don't reject. So it's going to look like this. Reject or don't reject. So it's going to look like this. Some of them I'll reject. Some of them I won't reject. Some I'll reject. I don't know, maybe it'll look like this. I'm just going to collect together all the not rejected things. So I'm going to take C to be the set of all theta such that when I treat this as a null hypothesis, I don't reject. So that the test unrejected things, yes.
For that probability over there that you said it's less than alpha, shouldn't be outer subindex be theta rather than theta 0?
No, because the type 1 error is the probability of rejecting when the null hypothesis is true. Any other questions? Yeah.
Are you making any assumptions about theta? Like, I don't want to say that's continuous.
No, no assumptions.
So I could have like rejected x is rational and accept that it's right.
Sure. I'm not saying you'll get a good confidence interval, but you'll get a valid confidence. So we have to, we'll come back to that point later, which is we have to separate, just like in tests, we have to separate controlling the type 1 error versus having a good test, which is high power, versus validity of the confidence interval versus how wide your confidence interval is. So we'll come back to that point. So first of all, I claim that this is a confidence interval. So I claim that no matter what the true value is, the probability that this traps the true value is at least 1 minus alpha. The proof is very simple. So pick any theta. Let theta be in here to denote the true value. The true value is something. I don't know what it is. Just call it theta. What's the probability that what is the probability that I fail to capture this? Well, I'm testing every value. At some point, I'm going to test this particular value. When I test that value, how would I not contain theta? Well, the only way I could not contain it is if that was rejected. Remember, theta, the confidence interval is the set of unrejected. So that means when I did this test, I rejected the null hypothesis. That's the probability that I rejected. But by construction, the probability, we did a size alpha test. The probability of rejecting theta when theta happens to be the true value is plus the root of alpha. We're done. That's all there is to it. The probability that theta is not in there is less than alpha. Therefore, the probability that theta is in here is greater than 1. So let me do some examples so that that's clear what we actually do. So this, by the way, this might sound computationally infeasible. How can I do infinitely many confidence tests? First, the good news is most of the time, you don't actually have to do the tests. You can figure out which things are going to be rejected, not rejected, without ever doing the test. So let's do some examples of that.
I have a question.
Yeah.
So, where did we get that probability is less than or equal than alpha again?
It's the definition of a size alpha test.
Oh.
All right, let's just revisit the normal example again, which we started with, but now we're going to do it from this point of view. So we had a normal, the sigma squared known. Sigma squared is known. Let's think back to some test of ours. We wanted to test, if I wanted to test a particular value, this was a case where we didn't have to even do an asymptotic approximation. But whatever test we did, the wall test, like they all came out to be the same in this case. That was, when did we reject the null? We rejected when x bar minus mu0 times root n over sigma was bigger than z alpha over 2, right? That was our our size alpha test. We get that. We got that several different ways. I mean, it's the Wald test, it's the like of the ratio test, it turned out to be, or you could just check that it's a level alpha test. So now I want to say, I want to find C What is C? It's the set of all values such that if I tested them, I wouldn't reject. It's the unrejected values. I don't actually need to do all the tests to see that. I can just look at this and say, for which values of mu will I not reject? Well, it's exactly when it's the set of all mu's such that this is less than this, such that root n x bar minus mu over sigma is less than this, which if I rearrange it, when is this less than this? Well, when mu is in the interval x bar plus or minus, it's exactly x bar plus or minus z alpha over 2. Right? If this, in the set x bar plus or minus this will be true, just by rearranging it, and conversely. So, just with a little bit of inspection, we see that if I were to test every value and collect together all the non-rejected values, I would precisely get back this interval. So you can think of that interval as coming about from converting the test. Okay, any questions? Let me do this one. So actually, yeah, I think what we'll do is we're going to do more examples once we combine this with large sample approximations, because in practice, we usually, just to simplify things, we usually base the test on an asymptotic test, so we get an asymptotic confidence interval. And so we'll come back and do more examples when I talk about large sample approximations. You don't have to, right? Everything could always be done. This is an important point. In principle, we never need to use asymptotic approximations because for testing the null hypothesis, all I have to do, when I'm testing a null hypothesis, I know the true value. I'm saying, what if the true value is 5? I could now construct a rejection set which has exactly 5% rejection rate. I could even do it by simulation of that. How big do I have to go to reject to make sure I have 5%? I can just simulate from that distribution. So in principle, I can construct a test for every value of the parameter. I can invert this test, and I'd have an exact finite sample, 95% confidence. It's just that you can see in practice that can be very tedious and time-consuming, which is why we use these large sample approximations. So I'm gonna come back to the inverting a test when we talk about large sample things. I do want to mention, do I want to mention pivots? Well, decide. You know what? I think we're going to make pivots optional. So section 4 called pivots. It's another way of constructing interval of confidence sets. It generally leads to the same confidence sets. That's why I'm kind of thinking it's probably not worth the time. So here's what I think you should read through it. It's not hard. And you're going to get the same interval anyway. But I think you should read through it, but I think I'm going to skip it in the interest of time. I'd rather go on to section 5, which is about now how do we combine converting a test with the large sample theory. And the answer is, well, it's going to lead to two, just like we had the Wald and the likelihood ratio test, we're going to have two confidence sets. So let me explain that. So we know that we often have the case, and I did this, I'm just repeating what I did earlier, that we often have some sort of central limit theorem, like for the maximum likelihood estimator, say. Although other estimators, besides the maximum likelihood estimator, often do have a central limit theorem as well. But we'll think about that as the MLE. It could be the method of moments, could be something else that we'll talk about later. That led us to the Wald test, which was to reject the null hypothesis theta is equal to theta 0 if theta hat minus theta 0 over the standard error. Okay, that was our Wald style test. The type 1 error is, at least as n gets big, alpha. And so if I invert the test just like I did here, that's it. We get the the corresponding confidence interval from inverting this large sample test is exactly what we wrote down a minute ago. It's the estimator plus or minus Z alpha over 2 times the standard error. So this is probably the most commonly used confidence interval. This is why you see in the New York Times these polls are some estimate plus or minus something. They're giving you a 95% confidence interval for the proportion of people that will vote for a candidate. Now, if you look at Nate Silver's website, he does something a little bit differently. So that one's a little bit more complicated. The standard polls are something like this, and the articles in Nature and Science have always estimates plus or minus something. This is what they're doing. So this is one of the most common, this little equation is one of the most common equations in science, you might say. Some sort of estimate, plus or minus, Z alpha over 2 times some standard error. It's an approximate 95% confidence. So if I take all of those confidence intervals over the years in Nature and Science, there's probably millions of them. What we know is that some of them contain the true value and some don't. And in principle, assuming there aren't biases and so on, about 95% of them will be correct. Here's another point. If I take alpha to be 0.05, and I'm not saying you should, but people often take that, which means we're talking about a 95% confidence interval. What is Z alpha over 2? It's 1.96. Boy, there's a number that should be burned into your memory. And here's an asymptotic approximation to 1.96. 2. And that's why you often see people report theta hat plus or minus 2 standard errors. You often see people say plus or minus 2 standard errors. It's just 1.96 is basically 2. So that's a very, very common thing to see people report. On the other hand, if we inverted the likelihood ratio test, we get something very, very interesting. So, and again, I'm going to use the asymptotic version. So what is the likelihood ratio test? So let's think about, let's think about testing theta equals a particular value, theta 0, versus theta is not equal to theta 0. So I'm not testing here that theta is in some subspace. I'm just going to test a particular value. So in other words, if this is the parameter space, and here's one point, that's the null hypothesis. I'm using a likelihood ratio test where the null hypothesis is now a single point, so it's dimension 0. So what is the rejection rule? The rejection rule is to compute minus 2 times log theta 0 over theta hat. If that's bigger than a chi-squared with, now how many degrees of freedom? So it's the difference of dimension. So if the dimension of theta was d, I guess I called it k, what's the dimension of the null? 0. So the difference of dimension is again k. So this would be k alpha. So the confidence set is the set of thetas that you would not have rejected. So that's just the set of thetas with this reverse inequality stream. The confidence set, now watch this, it's the set of thetas such that minus 2 times log theta with theta hat is less than this. I'm going to rewrite that. We're going to do that here. I'm going to do it here. I'm going to do it here because this is quite important. Anyway, this is missing from the notes, but this is important because I want to rewrite this confidence interval in a different form. I can rewrite this as L of theta over L bigger than half times this number. So what is that? What we're doing is we're drawing the likelihood function. Here's the likelihood function. Except I'm dividing it through by its maximum. Yes.
How did you get half times 3?
Let's see, right. It should be an E. Probably E. Is that better?
Minus.
Thank you. Like that? Okay. Yes, correct. The point is, this is a number. This is just a number. And this is the likelihood divided by its maximum. So we think of it as the normalized likelihood. It's just the likelihood so that the maximum value is 1. And what are we saying? The confidence set says we're finding all the thetas where the likelihood is bigger than some constant. So it's this. This is the likelihood ratio confidence interval. It says take the likelihood and chop it off somewhere. That's your confidence set. Notice that it doesn't have to be symmetric. The walled interval is the estimate plus or minus something. It's always symmetric. But if the likelihood, let's suppose the likelihood looked like this, and this is theta hat. When I cut across here, I'm not getting a symmetric interval. I'm getting an asymmetric. In fact, I could get a disconnected interval, right? If the likelihood was big in 2 places, I wouldn't even get an interval, like I said. In higher dimensional space, you could get a pretty weird looking confidence set. And you'll see this in a lot of articles. They'll draw a picture of the likelihood function, and the confidence set might be some weird looking set. That's fine. They're just chopping off the likelihood. So these are the 2 main ways in parametric inference to get the confidence set, which is the Wald-style thing, estimate plus or minus 2 standard errors, or based on the likelihood function, which corresponds to taking the likelihood and chopping it off at an appropriate constant. This constant comes again from inverting the test. We know that's just a number we can look up. And these are both asymptotic confidence sets, so that we don't know the probability that theta traps Cn, but we do know that it converges to 1 minus alpha as a
Since the likelihood ratio test gives sort of a test in some way, this is also good for test.
So one thing, it's a good question. We didn't talk at all, and I didn't put in notes here about optionality. Because you can make lots of confidence sets that are 95%. Here's one. Take the entire real line. I'm going to call that my confidence set. Well, that contains the truth 100% of the time. But it's not very useful, right? So if we were going to get into optimality, yes, we would talk about what of all the confidence sets that have coverage 1 minus alpha, which one is the smallest expected one? So there's a parallel theory, and we did it for point estimation. For example, we talked about minimax point estimators, and I mentioned you could try to find maximum power tests, although we didn't do it. And similarly, there's an optimality theory here too. The likelihood ratio confidence does have certain optimality properties under some conditions, but I don't want to say it's in general always optimal. But yes, it's generally a good confidence set in some sense.
So you just mentioned that this level sets might look very disconnected and really. The question is, how do you even judge how good that confidence interval is when it's not anymore something very regular?
Yeah. So if you get it's a good question. So suppose you have a really weird likelihood function. This happens a lot, actually, like in high dimensional problems. This very complicated surface, and your confidence set might look like this, some weird shape. There'll be another piece over here, another piece over here. So this happens in I have to say, like in climate science and in astrophysics, so on, the models are very complicated, and I have to say, it's a bit worrying, because people just, there's this tendency, no offense to the physicists, you know, there's this tendency of physicists to just do this chi-square thing and just say that's a 95% confidence interval. There's a good chance that if you're getting really weird confidence sets, that this asymptotic approximation is probably not reliable. You really shouldn't be seeing too much weird stuff. Because asymptotically, we also know you can prove that the log likelihood becomes asymptotically quadratic. And so when you see a lot of weird stuff, the truth is that's an alarm bell that maybe we shouldn't be using large sample things, in which case we should be going back and doing this from an exact finite sample perspective, which means you have to do a lot of simulation work. So this may not be a good 95% confidence interval. On the other hand, the fact that it's got these different pieces can be informative, because it might be telling you there are different regions of the parameter space that seem to be well supported by the data. There's no reason why the data should point you to this one area. It might be that these are pretty good fits too. So it's kind of telling you these fit the data well, but so do these and so do these. That's important information, actually. In fact, this is again one of the advantages over confidence sets over point estimates. You just end up picking one value, but that's, you know, very, very, very optimistic thing I can describe as one value. The nice thing about a confidence set is it's kind of showing you these are the values that are kind of consistent with the data, and if there's many different regions, you want to know about it. But whether you should trust whether it's truly 95%, that's the time to worry a bit. Okay. So, in fact, another thing that, just because I happen to work with physicists, I'm using physics as an example often, they'll do one set of experiments, say from a certain satellite, which will give them a confidence set maybe that looks like this. But then they might use a different type of data, or a different type of instrument, and it might give them a confidence set that looks like this. And the cool thing is that by combining these, you can often get more information. So combining confidence sets from different sources of information can often lead to much more precise inferences, and that's something you'll see done in practice. So I hope it's becoming evident. In fact, this is what we're going to talk about right now, which is tests versus confidence. So I did say I think that most of the time, and there's exceptions, but most of the time when you're doing data analysis, you want to use confidence intervals as opposed to tests. And I have this little example on page 6 to try to illustrate this point. So first of all, here's a simple theorem. You can prove this, which is the duality between test and confidence intervals. So we've already seen every test gives me a confidence interval. The reverse is also true. Suppose I already have constructed some way of getting confidence sets. So I have my confidence. That also gives me a way of doing a test, which is if I want to test theta equals theta 0 versus theta is not equal to theta 0, all I have to do is I reject the null. If theta 0 is not in the confidence set. And you can check that that gives you a size alpha test. So confidence intervals and tests are dual to each other. Once you have a test, you can construct a confidence interval. But if you start with a confidence interval, you can construct a test. And it's a very simple test. You make your confidence interval and you want to test whether theta is 0, you just check the 0 in there or not. So it's very intuitive. But now let me show you why I think confidence intervals are much more informative than tests. So I'll draw these 4 different scenarios. So let's suppose I want to test whether I'm comparing a drug to a placebo. So I'm testing the difference of the mean, say that's theta. I want to test if the knowledge probability is 0 or not. Or maybe I want to test whether I'm thinking of something that's been in the news. What have I seen in the news? Salt causes heart disease, or red meat causes cancer, something like that. And so often you'll see in the newspaper they'll say that it was statistically significant or was not statistically significant, which means you rejected the null or didn't. But that's terrible. Let's see why a confidence interval is much more informative. Suppose, let's look at some examples of confidence intervals. So here's a confidence interval. So according to what I just told you, this is the null value we're testing. Say we're testing 0. This is theta. We take values all the way along here. And I get this confidence interval. So what's the test? The outcome of the test? We reject, right? Because it doesn't contain 0. So we reject the hypothesis. But there's much more information there. Not only are we rejecting, we have a pretty good estimate of what this effect size is, and it's pretty accurate. Okay, so there's more information. How about, suppose, let's look at a second experiment. Suppose it came out like this. What we're going to see here, it excludes, this confidence interval excludes what we would reject. But now if I ask you, what's the effect size? I can say, oh, I have a very accurate estimate of effect size. And it's, how big is it? It's 0.000001. So formally, we've rejected the hypothesis. We said it's not 0. But we're very sure it's a very, very, very small number. So who cares? Right? That's called practically not significant. So there's statistically significance, but then there's practical significance. And this is what happened. Actually, that red meat one is a good example. If I remember correctly, a few months ago, there was this thing about red meat got classified in the same category by the World Health Organization as cigarettes. Okay? This is like insane. And if you actually look at the size of the effect, what they're saying is it was significantly hitting 0, but the effect was so small. So because the confidence interval was small, yes, it rejected the null hypothesis, it excluded 0. But the effect size was so tiny that it was of no practical significance. This is the confusion, again, between practical or clinical significance and statistical significance. Just saying it excluded 0 isn't telling you anything. How big is the effect? That's what you really want to know. Okay? Here's another example. Let's suppose we have one that includes 0. So this would say, do not reject the null hypothesis. And what you can see is this is a case where we just don't have much information. The confidence interval is huge. So the real answer should be, we don't know what's going on here. The confidence interval is huge. Is this substance bad for you or good for you? I don't know. Look at the size of the confidence interval. It includes 0, and it also includes mostly positive values. I'd probably say, yeah, well, it looks to me like there's a lot of positive values here. Maybe I'd avoid this thing, even though it's not statistically significant. And you can make up other examples like this. Here's one where it doesn't reject the null. So you say it's not significant, but not only that, I'm pretty sure if there is an effect, it's very small. Here's one where, I don't know, it could be really bad for me, it could be really good for me. And the correct answer is, just saying it's not significant isn't very informative. Saying we really have no idea what's going on is a much better summary. So I hope I'm getting across the idea that by reporting the confidence interval, it's just much more informative than just reporting whether you reject a test or not. Saying whether you reject a test or not is just telling you whether it contains a particular value. You're just throwing away so much information by just doing a test instead of a confidence. So this is, that's my plea for don't become one of those p-value people who just does a study and then reports the p-value and moves on to the next paper. You should be much better off. Oh, I see. I do have this thing about the I was just teaching from the wrong set of notes, so how about that? Okay. I had 2 copies of the lecture notes stapled together. I was teaching from the old one, so I was teaching a lesson. Okay, so this was, hopefully, was this in the notes? Yes, so okay, good. I did post it. Now, actually, let me pause and see if there's any questions to it. And so, to summarize so far, we're going to see later in the course that there's many ways to construct confidence intervals besides these confidence sets. But the Wald and the likelihood ratio, at least in parametric intervals, are the most commonly used things. So we'll use the bootstrap next week, a different method. Section 7 here is another sort of optional section. It's I wasn't sure whether to include it or not, so I'll just make it sort of optional. It's just showing you how to construct a confidence set for the CDF, for the cumulative distribution function. But we're going to talk about non-parametric intervals anyway next week, so, and it probably belongs more in the non-parametric setting, so I think we'll consider section 7 here to be an optional. Optional. Okay, it's both optimal and optional. Question?
You mentioned that the wall test is like a good, when you get the confidence interval to be something plus minus 2 times the standard error, it gives you a symmetric confidence interval.
Yeah.
Is that like common? Does it happen in real life, and that's why that's like used more commonly? Slash, what if you wanted to construct a confidence interval that wasn't symmetric?
So if you don't want a symmetric interval, I would use the likelihood ratio test, because that way if the likelihood function is skewed, you will get a non-symmetric interval. Technically what's going on is this. Both the likelihood ratio based confidence interval and the walled interval are asymptotically equivalent. So that means as n gets bigger, you're going to hit the same interval. In practice, though, for finite samples, it could be that one is more accurate than another. And I hesitate to say this, but I would say I've seen papers that have done simulations that suggest that the likelihood-based interval is usually a little more accurate than the walled interval, probably because the walled interval is forcing it to be symmetric. But I don't want to claim that's a theorem or something like that. So I think the walled interval, though, is more commonly used just because you can see it's really easy, right? Estimate plus or minus 2 standard errors, you're done. The likelihood interval, you kind of have to find the likelihood function and chop it across. But, if I had a bet, I would bet the likelihood ratio interval that it's probably closer to its 95% coverage more often. But again, that's just kind of a guess. But yeah, if the likelihood is very non-symmetric, you might want to use the likelihood-based interval. And it definitely won't be a symmetric interval.
What conditions could be the wall test more accurate, like time?
Is there conditions under which the wall test would be more accurate? I think, it's not easy probably to say that. I would imagine you could construct some scenario where you could show it's more accurate. But, so I'm saying there probably are situations, but they're probably not common. And I certainly don't know one off the top of my head. When n is pretty large, it shouldn't matter much which confidence interval you get. So by the way, like in most, if you use R, hopefully you're all using R now, if you run any statistical procedure, it often gives you both intervals, so you can compare them. And you'll see once n is moderately large, there shouldn't be much difference between the two confidence intervals.
What also, now that you mentioned R, what about, so if you have enough like sample points, right? What about, I've seen people sometimes just use the quantile and say, okay, the 97.5 and then minus the 0.25 to construct a confidence interval centered at, say, the mean.
That's getting closer to bootstrapping. And we're going to start, that kind of thinking is very close to using the bootstrap, which we will talk about next week.
Okay.
Yeah. Any other questions? Okay, I'll give back your homework. And the next week we're switching to non-parametrics. It's like I'm freeing you. I'm freeing you from the bonds of parametrics.